In hospital rooms around the world, patients lie waiting for a medical miracle they cannot control. When a vital organ fails, their survival depends entirely on a steady rhythm holding out long enough for a replacement to arrive. We first learned to defy this natural limit in the mid-20th century. Inside packed operating rooms, surgeons performed the first successful human-to-human organ transplants, a kidney in 1954, a heart in 1967. They proved that medicine could effectively restart a failing body. But this medical triumph quickly hit a mathematical wall. This graph plots the supply of human donor organs over time. The line remains virtually flat year after year. Meanwhile, the patient waitlist climbs, leaving a massive growing gap between people in need and available organs. The entire system operates on a painful irony. To save one life, doctors must wait for another human tragedy to occur. It is an economy built strictly on scarcity. To engineer a way out of this shortage, researchers initially turned to machines. Early prototypes like this mechanical heart, built from polymers and plastics, were designed to replace failing biology with continuous pumping hardware. When plastic couldn't fully replicate the chemical nuance of living tissue, science looked across species lines. The practice of xenotransplantation gained traction, aiming to use animal organs as human replacements. Pigs became the primary candidates due to their size and biological similarity. But to prevent the human body from instantly rejecting the foreign tissue, scientists had to edit the pig's DNA, rewriting it at the genetic level to silence the human immune system's defensive alarms. Yet, whether employing mechanical pumps or genetically altered animal tissue, these methods are temporary measures. They are ongoing battles against a human body that naturally wants to destroy anything that doesn't belong to it. What if we didn't have to scavenge for parts or borrow them from other animals? What if medical science could simply manufacture human organs on demand? This question led to bioprinting. Instead of molding inert plastics, this technology uses the precise manufacturing techniques of 3D printing to construct active biological material. Rather than melting plastic filaments, a bioprinter's needle deposits living cells. It uses a specialized bioink to build tissue, stacking cellular material drop by drop, layer by layer. This method shifts transplant medicine away from a reliance on random external donors toward a model of controlled biological manufacturing. The process begins by extracting a small sample of the patient's own cellular material. In a lab setting, doctors provide nutrients to force these cells to multiply, cultivating a massive reserve of personalized raw bioink. The bioprinter then follows a digital blueprint, laying down this customized biological material to form complex three-dimensional structures, like the intricate chambers and valves of a heart. Because the printed organ is built from the patient's exact DNA, the body recognizes it as its own. There are no immune alarms, no lifelong anti-rejection drugs, and no risk of the tissue being attacked. It directly addresses both sides of the transplant crisis. It solves the biological problem of immune rejection while simultaneously addressing the mathematical deficit of the supply shortage. When a heart or a kidney is printed from a digital file, the boundary between the natural and the manufactured begins to blur. Society will have to determine how to balance our deep physical drive for survival with the moral implications of redefining identity and pushing past our natural limits. But despite these ethical debates, the human imperative to cure disease is relentless. The potential to save lives ensures this technology will continue to advance. Ultimately, the science serves a very grounded reality. It is about a child receiving a new heart and reaching adulthood. It is about a parent surviving organ failure to see their children grow up. For decades, these stories relied on a system where one person's survival was dependent on another person's death. Bioprinting replaces that fragility with resilience. In time, this could significantly reduce the years spent on waiting lists, moving medicine toward a future where a failing organ is treated as a solvable manufacturing challenge rather than a terminal shortage. When survival no longer requires a donor, the phrase borrowed time begins to lose its meaning. It is no longer about borrowing a life from someone else. It's about a patient's own biology being renewed.